Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session of System Programming with Linux. Today we are going to have a first session on the subject of multi-threaded programming. The agenda for today's session is shown on the slide. First of all, we will have a quick review of the concept of concurrent and parallel programming. We will see the overview of threads and compare it with processes. We will discuss different thread implementation models and the Linux implementations of POSIX threads using the LinuxThreads and the NPTEL. After this theoretical part, we'll move on to practically creating and managing threads using the pthread API. We'll talk about the thread attributes and we will see how the threads behave when they receive the signal and the concept of fork and exit with threads and thread cancellation. Excuse me. Okay, suppose we want to add 8 numbers and there are 7 addition operations, and if each operation takes 1 CPU cycle, the entire operation will take 7 CPU cycles. So this is how the sequential programming goes on, and most of us are used to of doing sequential programs. Suppose we have 4 CPUs or a 4 core CPU, and in such a case the 7 addition operations can now be completed in just 3 CPU cycles. In the first CPU cycles, 4 addition operations will take place on the 4 different CPUs, and the resulting values will again be added on 2 CPUs in the second CPU cycle, and in the third CPU cycle the entire operation of adding the 8 values will be completed. Okay, so this slide shows you 3 different ways of achieving concurrency. And the first is you use fork to create a child process and let that child process do the task concurrently. But this technique do need the inter-process communication technique, and the other limitation is the lot of memory and time is required for process creation. We will talk about IPC in some future session in detail, inshallah. Today we are actually going to achieve concurrency using multiple threads within a single process. And of course this is speedy, as creating a thread is faster than creating a process. Moreover, no IPC is required. The third technique which we will talk about in the later part of this course is using non-blocking and asynchronous I/O using the select and the poll system calls. Let us move ahead and have a quick recap of threads before we make our hands dirty and start writing multi-threaded programs. Dear students, remember every process has 2 main characteristics, the resource ownership and the scheduling. And these 2 characteristics are treated independently by the operating system. The unit of resource ownership is referred to as a process, while the unit of dispatching is referred to as a thread. So to define a thread, let me say that a thread is an execution context that is independently scheduled but shares a single address space with other threads of the same process. This slide shows similarities and differences between processes and threads. We have discussed these in our operating system concept course as well. This slide shows a pictorial view of 2 processes. Over here on the left we have a process with a single thread, while over here we have a process having 3 threads of execution. Note that every thread has its own stack and register. While all the threads share the code section, data section and the open file descriptors. Excuse me. This is another pictorial view of the multi-threaded process having 3 threads other than the main thread. You can observe over here the process stack is divided into 4 parts. That is, there is a separate stack for each thread. Well, every stack needs a separate stack primarily for 2 reasons. The first is every thread need to have its own set of local variables, and the second is every thread may need to call different functions whose activation records need to be pushed on the stack and later popped. Well, dear students, over here in the code section as well, you can see every thread is executing its own part of code. So need to have its own program counter or instruction pointer. And finally, since all modern hardware architecture supports some form of pipelining, so based on that, there are 2 types of multi-threading shown over here, temporal and simultaneous. In temporal multi-threading, only one thread of instruction can execute in any given pipeline stage at a time. While in simultaneous multi-threading, which is also known as hyper-threading, more than one thread of instruction can execute in any given pipeline stage at a time. Well, this slide shows the division of different process attributes in a multi-threaded process. All the threads within a process share their IDs, the code and data section, global variables. Well, this is a typo. Error number variable is normally not shared. Every thread has its own. The interval timers, signal handlers, nice values, record logs, these all are shared by all threads. While every thread has its own thread ID, the entire set of CPU registers, stack, state, the error number variable, the priority, the CPU affinity and the signal mask. Okay, so before I talk about the 2 Linux implementations of the pthread API, let me touch upon some theoretical aspects and discuss 3 different models that can be used for implementing a threading API. The differences between these models is based on how these threads are mapped onto kernel scheduling entities. And the kernel scheduling entities are the units to which the kernel actually allocates the CPU. Let us first talk about the first thread implementation model, and that is ManytoOne. Well, dear students, in ManytoOne threading implementation, all of the details of thread creation, termination, scheduling, synchronization and so on are handled entirely within the user space. Kernel knows nothing about the existence of multiple threads within a process. The advantages of this model are the thread operations are fast as no mode switch is required. And secondly, user level threads can be used even if the underlying platform does not support multi-threading. The disadvantages of this model are when a user level thread makes a blocking system call, for example read, the entire process is blocked. And since the kernel is unaware of the existence of multiple threads within the process, it cannot schedule separate threads to different CPUs in case of a multiprocessor architecture. The other thread implementation model is one-to-one. In one-to-one threading implementation, each thread maps onto a separate kernel scheduling entity. All of the details of thread creation, termination, scheduling, synchronization and so on are handled by system calls inside the kernel. The advantages of this model: first is when a kernel level thread makes a blocking system call, only that thread is blocked. And since the kernel is aware of the existence of multiple threads, so it can schedule separate threads to different CPUs in case of a multiprocessor architecture. The disadvantages of this model are thread operations are slow as a mod switch is required, and the overhead of maintaining a separate kernel scheduling entity for each of the threads in an application places a significant load on the kernel scheduler. and thus degrading the overall system performance. Well, this is a third model, many-to-many, and this aims to combine the advantages of one-to-one and many-to-one model while eliminating their disadvantages. The main disadvantage of this model is its complexity. So the many-to-many model was initially considered for the NPTEL threading implementation, but rejected as it required much changes to the existing kernel code. The Linux threading implementations are LinuxThread and NPTEL, and they both employ the one-to-one model. Let's talk about these two implementations in a little bit of detail. The first is the Linux thread. Well, LinuxThreads is the original Linux threading implementation developed by Xavier Leroy. In addition to the threads created by the application, LinuxThreads creates an additional manager thread that handles thread creation and termination. Threads are created using the clone system call with the flags shown over here: clone VM, clone files, clone fs, and clone sighand. Well, there are certain deviations from the specified behavior. These Linux threads have these deviations from the standard Unix specification version 3. Most of these have been overcome by the new implementation, and that is the NPTEL. Please go through with these deviations when you have time. The native POSIX thread library, NPTEL. This is the modern Linux threading implementation developed by Draper and Ingo Molinar, and it is designed to address most of the shortcomings of the previous implementation, that is LinuxThreads. It adheres more closely to SUSE v3 specification. Applications that employ large number of threads scale much better in NPTEL rather than under LinuxThread. Over here as well, threads are created using clone that specifies these flags as well, other than the flags used by the Linux thread. And in case if you want to check out the implementation on your system, you can use this getconf command. Okay, so I think that's enough. Before I move on to the Linux terminal, let us have a very quick discussion on some of the basic functions that we are going to use to create and manage the threads. And before I talk about the functions, let me tell you that there are a lot of different data types that pthread API defines. For example, pthread_t is the data type that is used to identify a thread, to keep the ID of that thread, and we have others as well. Okay, pthread create. This is the function that is used to create a child thread and starts its execution. There are 4 arguments which are passed to this create function. On success, the thread ID of the new thread is returned in the first argument. The second argument is of type pthread attrt of this type, and this is normally null because we normally go with the default attributes of the new thread. The third argument is actually the thread function, and this is the function which this thread is going to execute. And the fourth argument is actually a pointer of type void, which points to the value to be passed to the thread start function. This can also be null if you do not want to pass anything to the thread function. And it can also be the address of a structure if you want to pass multiple arguments. Please do go through the man page of pthread create for details. The way pthread create is used to create a thread, you can use pthread exit to terminate a thread. There are different ways to terminate a thread. If the thread function calls the return statement, or the thread function calls the pthread exit function. In case if the main thread calls return or calls exit, even then all the threads within that process terminates. And lastly, if any of the thread calls exit, the entire process terminates. Well, we can place a null over here. If we do not place a null over here to the pthread exit function, uh, this will be the case when the thread function wants to return something to its caller, and that will be received in the pthread join function, which is shown over here. Pthread join function is just like the wait call which we are used to of in multi-programming with fork. The way we can wait for a child process using wait, similarly we can wait for a child thread using pthread join. And if we fail to do so, this will make the thread equivalent of a zombie process. There are two arguments. The first argument is the ID of the thread for which we want to wait, and the second argument can be null if some peer thread is not interested in the return value of the new thread. Otherwise, it can be a double pointer which will point to the status argument of pthread exit, which I talked about in the previous slide. Once again, do go to the man page of pthread join, and let me move on to the Linux terminal now and see some sample programs for the proof of concept. And let me first of all check out the glib C version we are using right now, using the getconf command, gnu underscore libc underscore version. Well, it is 2.24, and the lib pthread version, let me check out the lib pthread version as well. Lib, and it is NPTEL. Okay, and the GCC version is, I think, the latest one, and that is 7.2. And let me check the GDB as well. Well, it is 7.12. Remember, GDB version 5 and earlier are not good with debugging multi-threaded programs. And even with this version, that is 7.12, you cannot do post-mortem debugging as the core file does not correspond to the thread that crashes. Okay, let's see some basic program to understand the discussed concepts, and let me first show you a program t0.c. Okay, fine. Well, this is a program with a single thread of execution. This is not a multi-threaded program. The path of execution enters main and then enters the function f1 over here, which prints string PUCIT 5 times, each with a delay of 1 second. The path of execution then falls back to main again, and the control then transfers to function f2, which prints string Arif 5 times, each with a delay of 1 second again. And finally the control falls back to main, which prints bye bye from main, and it terminates. Okay, let me compile this program and run it. You see, first the function f1 is executing, printing string PUCIT 5 times, and after that f2 will execute, printing Arif 5 times, and then bye bye. The overall time taken by this process is about 10 seconds. Okay, let me show you a multi-threaded version of this program, t1.c. Okay, fine. Let me describe the code first. These are the two functions which are the multi-threaded functions. These functions will be executed by the newly created threads. Remember, the function name can be anything, but its signature should be such that it is passed exactly one argument and it returns one argument. Let me show you the man page of pthread create, and you see this thread function is a pointer actually which points to a function which is passed exactly one argument of type void pointer, and it returns one argument of type void pointer. Okay, fine. So this is important to understand, and your signature should always be like this for a multi-threaded function. Then I have created two variables of type pthread underscore t to keep the thread IDs, and this is the pthread create function which is going to create two threads. This null shows that we are interested in a thread with the default attributes, and this first thread will execute the function f1, and this second thread will execute the function f2, and we are not passing anything to these functions. And later over here I am calling pthread join twice. This main thread is joining the thread having the TID 1, and then it is joining the thread with TID 2. And this null over here shows that this main thread is not interested in the return value of this thread or this thread. Okay. And these functions are the same. This f1 is printing PUCIT 5 times with a delay of 1 second, and this is also printing Arif with a delay of 1 second. So now you will see that this code will execute concurrently. One thread will execute this function and the other thread will execute this function. And the total time taken by this program now will not be 10 seconds, rather it will be 5 seconds. Let me compile it first, t1.c, and remember, whenever you are writing a multi-threaded program, you need to link it with the library, that is lpthread. Let me execute it now, and you see both the threads are executing concurrently, and the time taken by it is of course 5 seconds and not 10 seconds. Okay, so let's see another example now. t2.c. Fine. Well, this program is also creating two child threads and then joining them, and one thread is executing this function f1 which is printing x 1000 times, and the other thread is executing this function which is printing o 800 times, and both these threads will execute concurrently. So you will see a stream of x's and o's on the std out, while the main thread will join these two threads, and after these two threads terminates, only then this main function will print this line bye bye from main thread. Let me compile and run this piece of code, t2.c -lpthread. You see, both the threads have executed concurrently, printing 1000 x's and 800 o's. Let me run it again. You see, it has executed concurrently. Let's see another example where we can pass some argument to the thread function. Let me open the code file t3.c. Okay, so this is a program with minor variation. Here we are receiving two integer values via command line arguments, that is the count of x and the count of o's. The main thread is creating two child threads, and we are passing some arguments to this thread function. Remember, the fourth argument to pthread create is actually the argument which will be passed to the thread function, and it should be of type void pointer. So over here I am passing this count of x to f1 and count of o to f2, and remember I am casting it to a void pointer. And over here in the function f1, I'm receiving that argument, casting it back to an integer and running the loop that much number of times. That is printing x's, and this is running the loops that much number of times and printing o's. I hope the logic is clear. I'm just showing you how we can pass arguments to a thread function. Let me compile this program now. GCC t3.c -lp thread. Let me clear screen and run this program with a value of, let's suppose, 10 and 20. You see we have 10 O's and 20 X's, and I can run it with 10 and 200 and 200. So there is no context switch between the threads, and if I run it for let's suppose 800 and let's suppose 1000, so there you might see context switches. Yes, you can see the context switches. No? There are no context switches. Let me run it with a bigger value, let's suppose 900 and 1500, and now you can see the context switches. We have some X's and some O's, and then some X's and then some O's. That's fine. So now we know how we can pass arguments to the thread function. Now the question is, what if we want to pass multiple arguments to a thread function? Let me show you another program, t4.c. And remember, in case if you want to pass more arguments to the thread function, you need to create a structure. You need to bundle up the arguments in a structure and pass a pointer to that structure to the thread function. So I have created a structure containing two members, the character to be printed and the count of the characters to be printed, and the rest logic is same. I have created an instance of this struct and places an x with a count of 1000. I have created pthread create, and I have passed a pointer to this structure, cast to a void pointer, and then I have created another structure and passed this to this function. And over here I don't need two functions now, there is just one function, and it will be passed this structure containing the character to be printed and the count of the characters to be printed. So this is the loop which runs a count number of times, printing whatever character is there in that structure. Once again, dear students, remember, point to be noted is we need to cast whatever we want to pass to the thread function to a void pointer, and while receiving that we need to cast it back to the appropriate type. Let us compile this program, clear screen and run it, and you see the program has executed successfully. Excuse me. Let us fall back to the slides. Okay, so now we know how to pass arguments to thread function. Let's see how we can return value from a thread function. Well, dear students, a thread function can return a pointer to its parent or the calling thread, and that can be received in the second argument of the pthread join function. The pointer returned by the pthread exit must not point to an object that is local to the thread, since that variable is created in the local stack of the terminating thread function. Moreover, making the local variable static will also fail, and that will be in the case if two threads run the same thread function and the second thread override the static variable with its own return value, then the return value written by the first thread will be overwritten. So never use a static variable inside a thread function. So what is the best solution? The best solution is to create a variable to be returned in the heap instead of the stack. Let's see some sample codes. of multi-threaded program that do some computation and return that value to the calling thread. Move on to the Linux terminal and see a program rv1.c. Okay, well, fine. Well, this program receives two integers via command line and compute the two nth prime numbers. We will receive two command line arguments which will be integers, and the thread functions will be passed these arguments, and they will compute and return the nth prime numbers. And you all know that the first prime number is 2, second is 3, third is 5, and so on. And if this program is passed, for example, 5 and 10 via command line, it will display the 5th and the 10th prime number, which are, I think, 11 and 29 respectively. And for this task, the main thread creates two child threads over here and joins them. Note the second argument to the pthread join is a double pointer of type void. When the thread function calls a pthread exit, which is the only argument to pthread exit is received over here in rv1 and over here in rv2. We cast them back to appropriate data type and we print that. So this is the code of the main thread. Now let us quickly discuss the code of the thread function as well. Remember, both the threads are going to call this same code. Well, this thread function receives the integer in variable n over here. Then it will create a variable candidate in which it is going to keep the result, and remember this has to be created on the heap. This while loop continues decrementing n. This continues decrementing n on occurrence of every next prime number, and this is happening over here. On occurrence of a prime, it is going to decrement n. And when n reaches 0, it calls pthread exit with the prime number. Over here, this for loop is actually doing the main task. It is actually determining if the number in the candidate, which is initialized with 2 over here, is a prime number or not, by searching for its factor until its square root. And we know that if a number doesn't have a factor until its square root, then it is a prime number. So if the number in the candidate is even, then we set the is prime to 0 and break this loop. And if the candidate has a factor, then also we set the is prime to 0 and break this loop. And if this loop breaks and we still have a 1 in the is prime, we decrement n as shown over here. This while loop breaks when n reaches 0, and the thread function calls this exit. Otherwise, we of course increment the candidate and repeat. Okay, fine. I think the logic is clear. Let me compile this program, rv1.c -lp thread. Yes, we are using the square root function of the math library. I need to link the math library as well. And let me pass 1 and 2 to be very simple. The first prime number is of course 2 and the second is 3. And let me pass 1 and 5. And the first is 2 and the fifth prime is 11. Let me pass 10 and 500. Okay, 10th is 29 and 50th prime number is 229. And let me check out the 100th prime, 101th prime number and 501th prime number. So these are those. And of course, this is a multi-threaded program. Both the threads executes concurrently, and if you extend the same program, finding a lot of different prime numbers by creating a lot of threads and compare it with a single threaded program, you can easily come to know the difference between the performance of a single threaded and a multi-threaded program. Let's see another example. rv2.c. Okay, so what is it doing? Okay, fine. Well, this program is receiving two file names via command line arguments and creating two threads by passing a file name to each thread function. The first argument, which is a file name, is passed to f1. The second argument is again passed to the same function, and the main thread joined with these. And remember, the pthread join has its second argument, which is a double pointer of type void, and we cast it back to an appropriate type, and then we display the output. And actually what this thread function is doing, it is just counting the characters, the number of characters in the file, and the main thread is of course displaying those characters. And the code is again very simple. We just open the file. First of all, of course, the thread function receives the argument, typecast it to the appropriate type, create the variable for result in the heap, opens the file, reads the file character by character, and increment result until the end of file is reached. And finally, pthread exit returns the number of characters in that file which are received over here, and then are printed on stdout. Pretty fine. Let me compile this program. gcc rv2.c -lp thread. Let me run it with two files, a small file and a long file, and you see the number of characters in the small file are 67 while in the long file are 18258. Let me confirm it using the word count program on the same two files, and you see small file 67 and long file 18258. Okay, so far so good. Let us fall back to the slides again. Okay, creating arrays of threads. Well, dear students, you may need to create large number of threads for dividing the computational task as per your program logic. Right now we have just created two threads. At compile time, if you know the number of threads you need, you can simply create an array of type pthread t to store the thread IDs. But if you do not know at compile time the number of threads you need, you may have to allocate memory on heap for storing the thread IDs. Oh, well, remember the maximum number of threads that a system allows can be seen in this file, which can of course be changed. proc syskernel thread max. Let me show you some sample programs which I have prepared for you. Let me show you array threads 1.c first. Okay, well, this is a very basic program. Over here the main thread receives okay, over here the main thread is creating an array of type pthread underscore t to have the IDs of 5 threads. Then I'm entering in a loop which will run 5 times and call pthread create and pthread join. And each time the pthread create will run, it will store the ID of the child thread in this array on the 0th index, 1st, 2nd, 3rd and 4th index. And all these threads are executing function f1, and for the first thread we are passing this string thread 1 to it. For the second thread we are passing this string, and so on. And the thread function is very simple. It is just receiving the string and printing I am child, for example, thread 1, thread 2, and so on. And after all the 5 threads are done with their execution, this line will be printed on screen. Let's compile and run this program. Array threads 1.c ./a.out. Well, that is great. So the way I have created 5 threads, you can create 100 threads. Let's see another example when array threads 2.c. Well, over here the main thread is receiving an integer via command line and converting it to an integer, storing it in this, and over here we need to create an array of type pthread_t on the heap to store the thread IDs, and this loop runs this much number of time to create this much number of threads. And over here I'm just passing the index I, the loop index I, to the thread function, and the thread function is just printing that loop index I. Fine. This is just another version of the same previous program, but this time it is creating the threads dynamically on the heap. GCC array threads 2.c ./a.out invalid. Let me create, let's suppose, 5 threads again, and you see 5 threads are created. Okay, let's see one more example, a constructive one, a good one, which you will enjoy. Array threads 3.c. Well, this program receives an integer via command line over here and creates 3 integer arrays of this size on the heap. So 3 arrays will be created. Then we are getting the input from the user in the first array, and then we are getting input from the user in the second array. Fine. And then we are going to create this much number of threads on the heap. We are calling the pthread create function this much number of times, and to each thread function we are passing the index of the thread, that is I. And actually what the thread function is doing, it is receiving that index and it is summing up the 2 appropriate location of the 2 input arrays and placing that result in the third array. Remember, dear students, we have created 3 arrays. We have got input or data in these 2 arrays, and this is the result array, which is the sum of these 2 arrays. So this makes sense. So if we have arrays of size 5, so there will be 5 threads, and each thread will be performing just one sum operation. And if we have an array of, let's suppose, 1000 elements, so there will be 1000 threads, and it will give you a real performance gain. I think so. Finally, the main thread, of course, will print the result on stdout. Let's compile this program. Clear screen and execute it. Okay, so let me give just 3, an array of 3 integers, and give me data, let's suppose 2, 4, and 6 in the first array, and 5, 3, and 1 in the second array, and you see the sum is 7, 7, 7. 5 plus 2, 7, 4 plus 3 is 7, 6 plus 1 is 7. So that's great. Fine, let us fall back again. Okay, well, this is your home task in which you need to write a multi-threaded program for matrix multiplication. I hope if you have understood the session so far, it will be a piece of cake for you. Okay, so well, we all know that error number is a global per process variable used to store the error number occurred in the last failed system call. What problem can occur due to this shared variable in a multi-threaded program? The answer to this question is a lot of problems. The problem is actually that if two or more threads come across some error, the same error number variable will be set. One thread may overwrite this global error number variable. And once the first thread checks this error number variable, it might have been overwritten by the other thread. And the solution is to make the error number local to every thread. And this can be achieved by compiling your code with -d_reentrant flag. I have not done it so far, but please, whenever you compile a multi-threaded program, do give this flag to GCC. Other than creating a local error number for every thread, it has two more advantages. One is that library functions are no longer defined as macros, and the second is the reentrant versions of the standard library functions are used. I will talk about the reentrant functions in some later session of threads when we will talk about the race conditions and the critical section problems, inshallah. Okay, well, in a multi-threaded process, all threads have the same PID as returned by the getPID system call. The question is how to uniquely identify a thread within a multi-threaded process. Let me straight away move on to the terminal and show you some sample programs for this. Let me just compile this program, id threads1.c. Let me show you this program on screen and let me run it. Okay. Well, fine. So this program is going to get the process ID using the getPID system call, which is shown over here, 19910. This is the PID of this process A product. And later I'm going to make another system call, that is the getTID. Remember, dear students, this getTID system call do not have a C wrapper, so I'm calling it using the syscall system call instead. Well, over here you can see the thread ID of the main thread is same as the process ID of the process. So remember, whenever the main thread calls getTID, it will get the PID of the process. The main thread is going to create two threads and then it is entering a while one loop, and every thread is again calling getTID. And when a thread calls getTID, it gets its own thread ID, which is over here 1911, and the other thread is having the ID of 19912. Okay, so let me move on to this is the PID of the process. Let me cd to proc, and inside proc let me cd to this directory. Okay. Well, over here you can see this task directory. Probably I have talked about this in some previous session as well. Let me ls this directory task, and you see over here we have further three subdirectories. 19910, which is the ID of the main thread, or the PID of the process as well. 19911 and 19912, which are the thread IDs of the child threads, the two child threads that we have created over here. So, my dear students, note that the task subdirectory has a subdirectory for every thread in the program. Here we have 3. Please do dig out details about the prop directory, and let me show you another program that is id threads 2.c. Okay. Well, this sample program gives you an understanding between the thread IDs returned by the get PID and the pthread self function. Well, over here, the main thread is creating 3 child threads and joining them. All the threads are executing function F1, and every thread is passing a string to this function. And over here, the thread function is actually using the get PID function to get the ID, the get TID function to get the thread ID, and using the pthread self function to again get the thread ID. So what I'm going to discuss is what is the difference between the IDs which we get from get TID system call and the pthread self library call. Okay, so let me compile this code, id_threads2.c. Let me link it as well. Let me get this program so that you can see it once I run it. Okay, so you see here, note the get PID. When called from a thread, always return the process ID. So when called from thread 1, it returns 19957. When called from thread 2, it returns 19957, and from thread 3 as well. Well, this get TID. The get TID returns a thread ID as assigned by Linux kernel, which is quite similar to the process ID and is reused after a very long time, like the PIDs. So you can see the thread ID of this thread, the child thread, is 19958, 19959, and 19960. And finally, this pthread self. This pthread self returns the thread ID as assigned by NPTEL thread implementation library, which is a very long number, unique within a process only. Here you can see the same thread ID, 8592, 8592, 8592. As it reuses the ID whenever the thread terminates. So as soon as this thread terminates, this thread ID is used again. Okay, I think enough for the thread IDs. Let us fall back to the slides again and see what is left now. Okay, thread attributes. Fine. Dear students, now let me talk about the second argument of the pthread create function, which we have used null so far. Every thread has a set of attributes which can be set before creating it. These are some of the attributes which can be set. For example, the detachstate, the stack address, the stack size. It is always recommended to not to change the stack address and stack size, and let it be system dependent. The priority policy and the scheduling attribute, that is inheritsched. Let me talk about the detachable and non-detachable thread attribute first. Well, dear students, a joinable thread like a process is not automatically cleaned up when it terminates. The thread's exit status hangs around in system until another thread calls a pthread join to obtain its return value. Only then its resources are released. For example, whenever we want to return data from child thread to parent thread, the child thread must be a joinable thread. This is a way of avoiding zombie threads. A thread can also be a detached thread. Well, remember, this is the default behavior. This is the default attribute. On the contrary, a detachable thread is cleaned up automatically when it terminates. Since a detached thread is immediately cleaned up, another thread may not wait for its completion using the pthread join to obtain its return value. For example, suppose the main thread creates a child thread to do a backup of a file, and the main thread continues its execution. When the backup is finished, the second thread can just terminate. There is no need for the main thread to join that child thread. A thread can detach itself using the pthread detach call as well later on. But if in the beginning you want to create a thread detachable, you can always set the attribute object of the thread. And these are the 5 steps you need to follow whenever you want to customize the thread attributes. First of all, you need to create a pthread attrt object. You call the pthread attr init function on it to initialize the attribute object. You modify the attribute object by using the different setters. Then you pass the pointer of that attribute object to the pthread create function, and finally you destroy that pthread attribute. Well, do see the man page for pthread attribute init and pthread attribute destroy. And there are a lot of getters and setters which are available for changing these attributes. And let me show you a program that changes the detached state, default detached state of a thread from joinable to detached. Let's move on to the terminal and see this program to understand it fully. Threads.c. Okay. Well, this program shows how to create a thread with attributes other than the default. It creates a thread attribute object over here, initializes it with the default attributes, and then it changes one attribute by using the setter, set detached state. And the attribute changes pthread create detached. And finally we pass this attribute object to the thread create function in the second argument. And up till now we have placed a null over here. And finally you just need to destroy it. And just for a proof of concept, I have just made the main thread enter in a while loop until the thread function has set this variable thread finish to 1. So I think this should run successfully. -np thread. Fine, you see this is a detached thread now, although I'm letting the main thread work so that the child thread should finish. Let me fall back to the slides again. Okay, dear students, signals and multiple threads. This is a confusing issue. You should have a clear concept that the Unix signal model was designed with the Unix process model in mind. So there are some significant conflicts between the signal and thread models. Combining signals and threads is a complex issue and should be avoided whenever possible. But from this course perspective, there are some key points that you should keep in mind. And these are: signal handlers are per process, signal masks are per thread. Sending a signal using kill command or the kill system call will terminate the process. And you can use pthread kill to send a signal to any other thread in the same process. And lastly, if one thread ignores a signal, then that signal is ignored by all threads. Okay, the other issue is with the exec. You must write down sample codes to understand the concept that if in a multi-threaded program one of the thread calls exec, what happens? And finally, what happens if in a multi-threaded program a thread calls fork? Is the child process single-threaded or multi-threaded? Well, let me read it out for you. The child process is created with a single thread always, that is the one that called the fork. Dear students, it is recommended that a fork in a multi-threaded process should always be followed by an immediate exec call, so that all global variables as well as all pthread objects disappear, as a child program overwrites the memory of the process. If there is no exec after the fork, then the state of the global variables as well as all pthread objects are preserved in the child, which may cause problems in the child program. So for programs that uses fork that is not followed by an exec, the pthread API provides a mechanism for defining fork handlers using the function pthread at fork. Please do write sample codes that make your concepts clear about the use of fork in a multi-threaded program. And finally, there is another call that I want you to explore at your own, and that is the pthread cancel. And this call is used by a thread to request that another thread should be cancelled. Well, this cancellation may cause a problem if the target thread is holding some resources which it must free later. And to counter this possibility, it is possible for a thread to make itself cancelable or uncancelable by calling a function pthread set cancel state. And if it makes itself cancelable, then it can have two different cancel types which can be set using the pthread set cancel type function, and which if asynchronous, then that thread may be cancelled at any point of its execution, and if the cancel type is deferred, in that case the cancellation request is queued until the target thread reaches the next cancellation point. Please do write down code that make the proof of this concept. Okay, dear students, that was a long session, and I still am leaving the issues or problems that you may come across in a multi-threaded program when the threads are updating shared variables. We will discuss these concepts inshallah in some next session, in which I will touch upon the synchronization part. I hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.